Okay, today we're going to talk about stationary points. For sketching polynomial functions, we basically need four things. We need the basic shape. Okay, so if you're talking about a quadratic, is it one of those shapes, or if it's a cubic, is it one of these shapes here, or one of those. So just need the basic shape of the graph. What its y-intercept is, what its x-intercept or x-intercepts are, plural, and things called stationary points. And you might have known those as turning points, they're points of inflection. They're places where the gradient of the graph equals zero. A stationary point is a point on a graph where the function momentarily stops rising or falling, increasing or decreasing, so sometimes called. That is a point where the gradient equals zero. So any stationary point is where the graph has a gradient of zero. So here, you can see here's a parabola. The function stops falling and starts rising after that point. So you can see, if I looked at the gradients here, I've got a negative gradient here, and at that very point, at that stationary point, my gradient is a horizontal line, which is zero, and then we start rising again, we get a positive gradient to the other side of that stationary point. Same here, this is an inflection this time. Sometimes I don't draw inflections all that well, but it stops rising momentarily, okay, and then it starts to rise again. So we've got positive gradient, it's rising with positive gradient, it momentarily stops there, and we've got a gradient of zero, and then it starts rising again, positive gradients. It's another type of stationary point. F of x, the function has stationary points when the derivative equals zero. Okay, so how do we find a stationary point? And this leads to our practical questions soon, our applied questions. Now, how do we find a maximum or a minimum? You make the derivative equal zero. Okay, so we're talking about f of x. F of x. You've got stationary points when f dash x equals zero. If our equation is y equals, it's when dy dx equals zero. Either way, it's when the derivative equals zero. You've got a stationary point. All right. If f dash a equals zero, a stationary point occurs when x equals a. Okay, so if you put an x value into derivative and you get zero, okay, that value for x represents a stationary point. To find its equivalent y value, you'd put that x value into the equation. So y would equal f of a. That is putting a into it. So therefore, a and f dash a would be a stationary point. Okay, so in other words, the x-coordinate and putting that x-coordinate into the derivative gives you a stationary point. Beg your pardon, there's a little error there. Putting a and into the actual equation gives you the stationary point, not in the derivative. Beg your pardon. Right, so just go over that again. So if f dash a, that is the derivative equals zero, you've got a stationary point at that x-coordinate equals a. To find its y-coordinate, you just put a back into the original equation, okay, and you'd find its y-coordinate, f of a. I'm now going to show you four different types of stationary points. First one's called a local minimum, and you would have seen these last year, okay? And a local minimum's characterised by having negative gradients to the left of it, a zero gradient at the actual point, in this case it's A, and then positive gradients to the right. So I've put here that distinctive pattern, negative, zero, positive. So gradients go from negative to zero to positive. That characterises a minimum. A local maximum is the opposite. Okay, so here's our A, it's our x-coordinate that gives us our maximum. To the left of that we've got positive gradients, then we've got zero gradient, and then we've got negative gradient. So that distinctive pattern, positive, zero, negative, characterises a local maximum. The next one is a point of inflection, a positive stationary point of inflection. So as it flattens out here, this graph, just for a second, there it is. I shouldn't use that language, but just at that moment, we've got a gradient of zero. To the left and to the right of it, the gradients are positive. So that's a distinctive pattern here. You've got positive, zero, positive again. Okay, that characterizes a positive point of inflection. You've got increasing, zero, increasing again. Then there's the negative point of inflection, where you've got a negative gradient, a zero momentarily, a negative gradient again. That pattern there, negative, zero, negative, is what a negative stationary point of inflection looks like. Okay, so you've got the gradient equaling zero just there. Alrighty. Careful, not all points of inflection are stationary points. Okay, you can get, you can get those sort of points, those sort of graphs where that there is not, does not have a zero gradient. Okay, it's just a negative gradient all the way. Okay, so just be careful of that. To determine a stationary point, we use a thing called a gradient table, and I'll cover that in the next video. So that's an introduction to stationary points.